Hi, in this video we'll be talking about a nice problem solving idea. So without any further delay, let's get into the problem. So you're given an array A of size n, initially all zeros, the array is all zero. You are given q queries to be done on the array. Each of the query has the form plus LRX. Okay. Now what is this LR and X given to you? So for this particular query, you need to do that, you need to add X, the value X given to you in all the indexes from range L to R. So in all the indexes L to R, you need to add the value X. Okay. And after all q queries are done, so there are q queries of this form. After all the queries are done, you need to print the final array. Okay. So that's the whole problem. Let's quickly look into what this means. So suppose you are given an array of all empty zeros initially, and you are given such queries. So let's say you need to add this 1 to the range 2 to 4, right? 2 to 4. So what eventually happens is that all these values become 1, right? All these values become 1 because you are adding 1 to this range. And then from range 1 to 5, you need to add 3, right? So for 1 to 5, you need to add 3. So these two becomes 3, right? These two become 3, but there was already a 1 over here. And then when you add 3 to this range, these values change into 4, right? These value would convert into 4, right? Now there is another query, let's say plus 0 to 2 x, right? And x is 2. So you add 0 to 2, the value 2. So all of these things change. Okay, so this will become 2, 5 and 6, right? 2, 5 and 6. So we just change that, we write 2, 5 and 6, right? And this is the final array that is there after all the queries have been processed. So after all the queries, you need to print this final array. Okay, so one obvious way to do this would be for every query you loop over the range you are given and just add x, right? You can loop over from L to R and just keep on adding x. So for that, for every query, on the worst case, you will need order n. Why? Because the range can take the whole of the array, right? The range can take the whole of array. So we cannot really do this because things would be like it would take q times the order n. There are q number of queries, and this would be order q into n, right? So this is like a brute force solution. We want to do something better than this. Okay, so how do we improve on this idea? So I will be making a claim first. Okay, I will be making a claim. So let's do few steps. Okay, so step 1 would be to create a new array of size n with all zeros. Okay, just we create a new array which is all zeros and that has a size of n. Okay, now for each of the query given to you that is of the form plus LRX, okay, what you do is that whenever you get this query in this new array, you change the value at index L by adding x to it, and you change the value at R plus 1 by subtracting x from it. Okay, so for every query you do this. So one of the query comes, you perform this operation, then the next comes, it has separate L and R, so you perform that accordingly, and you do this for all the queries. Now after all the queries are done, you just build the prefix sum array of the p that is being at the present state. Like after all the queries, the p values would have been changed, right? So whatever the values are, you just build the prefix sum array. So you just take a prefix sum of the array p, and you can do this in place because you can just loop from I equal to 0 to n minus 1 and keep on building the prefix sum of ith index, because you know that we can use the value at I and the prefix sum of I minus 1. So we have both the values, so you can build the prefix sum in place if you want. Okay, and voila, you have the final p that is actually the answer. Okay, so the p that you create with this process, this 3-step process, is your answer. Okay, so now let's look at an example run of that. So let's say you take this, you have 2, 4, 1, right? So we are doing this, we are performing this steps of algorithm that you're given 2 and 4. Okay, so you add 1 to 2 and subtract 1 from 4 plus 1, that is 5, right? Now these are the values currently, okay? So initially it was all zeros, okay? So these are values getting added, okay? So these two things were added. Then in the next query you are given 153, 1253. So you add 3 at 1 and you subtract 3 from 5 plus 1, that is 6, but you don't have that index, right? However, you don't even need this index. Why? Because we know that the final p array that we are getting is the answer, and we only need the first n minus 1 index, so we don't really care about the next few indexes. So you can just ignore the subtraction part because that's not really in the range from 0 to n minus 1, okay? Now after you have built this, let's look into the last query. So you have 0, 2, 2. So you need to add 2 to the range 0 to 2. So what you can do is that you can add 2 to the 0th index, and if you need to subtract from r plus 1, that would be 3, and you subtract 2 from 3, sorry, you subtract 2, right? And the index is 3. And now we need to just add these values, so that would be the corresponding values in the p array, right? Those are the corresponding values in the p array. So now let's just add these values. So let's clear off these zeros that are there in the array, and so we were doing these operations of plus x in the array itself, right? So the values would be 2, 3, so addition of everything that we have done till now. So I was just writing it in a different way, but that's just this, right? So this is what we were doing till now, and now what we do is that we build the prefix sum of this array. So that was our step 3, right? Let's quickly build the prefix sum of this. So the prefix sum of this would be 2 over here, okay? So 2 is over here. Now this value would be the sum of all of these things. So this would be 5, right? This would be 5. This would be 6. Right? Then this would be 4. This would be 4. And this would be 3. Right? So if you see, these are the actual values that we had earlier as well by using a brute force. So this is actually creating the correct array, right? This is actually creating the correct array, this algorithm. Now let's ask the main question: why is this claim even working? What's so special about this claim? Why is it even working? This seems like some magic, right? So to understand this, we need to understand how doing a plus x or minus x at individual positions in the array, how does that reflect once we do in place prefix sum, or if we build a prefix sum over that array, how does that reflect? So suppose you are doing a plus x at a particular position, right? You are doing plus x at this position, right? Now let's say we want to build the prefix sum. So the first value would be 0, right? This would be 0, right? So we don't write anything, so let's say we just keep it over there like that. Now this would be x, so the prefix sum value over here is actually the sum of all of these things, right? So this would be x, okay? So this would be x, okay? Next we have this value, so this cell would be sum of everything till this, right? This cell, so that is also x because everything over here that is empty is 0. So this range contains only this x, so this will be x as well. And you can see that for every other range as well that you can think of, like this range or anything else, like any other range going beyond this, everything contains x, right? Only the x. So the first cell is 0 and everything else is x. So we basically get something like this, that once you have this x, you get a contribution of x in all these cells when you build the prefix sum. Now what if we do x, a plus x over here, and what if we do a minus x over here? What do you think will happen in the prefix sum array? So if we look into this, this again is empty, so anyways prefix sum would be 0. This cell up to, if you talk about up to this cell, it contains only x, so this would be x, right? If you talk about things up to say this or this, right? So these ranges only contain this x, so even these values would be x, right? Now let's talk about this one, that this range up to this range, right? Now this contains both x and minus x, and rest everything is 0. So when you add all of these values, it turns out to 0, right? So this contains 0 and this contains 0, right? Because again, for this range as well, both of them will be contained, so both of them will cancel out, right? So this would look something like this, that you have the contribution of x only in this range. So this is the idea that we are using, that once we do a plus x over here and a minus x over here, at the end, if we build a prefix sum, the contribution for this will only last in this range between the first x to the last x minus x, right? And this is what we are using in the property, as a property to support this claim, that's why this is working, right? So this is how prefix sum array manifests itself once we add the contribution at particular positions. Now let's say we add a plus y after this. Let's say we add a plus y. Now what do you think will be the prefix sum array of this? So this will contain 0, this will contain x plus y with obvious reasons because it's from 0 to this. This will contain x plus y, this will contain x plus y. Now what does this cell contain? So this cell contains the sum of this range, right? And sum of this range is y, right? X and minus x gets cancelled and y is there. So this is y and this is y as well for the same reasons. So as you can see, adding this y in this cell itself and then building a prefix sum is same as adding y separately in that array where it had all x's, right? So from this we can understand that even two different queries don't really affect each other because we are just adding everything up. So we are basically doing the addition in a distributive fashion, that's it. We are just changing the order of operations, that's it. So the final array won't change in this operation, so you will get something like this itself, right? So let's look at what the time complexity of this approach is, and like, did we improve on the actual brute force one? So we create the new p array which contains all 0. So this is like an order n step, right? You need to create just a n sized array. Okay. Now for each of the query you do this. Now there are q queries and for all of them you do this operation, but these are just order 1 operations, right? They are just changed to 1 indexes in the array of p. So these are order 1 operation. So combined step 2 takes you order q, right? Combined step 2 takes you order 2, this whole part over here, this takes you order 2. Now step 3, build a prefix sum. Now we know that we can build prefix sums in order n. So this would take, step 3 takes you order n. So these are sequential steps, right? So the total time complexity would be n plus q plus n, that is order n plus q, right? Which is far better than n into q, right? Because both of them can be pretty large. So this is a technique which is called partial sums. So what we are doing over here is that keeping a partial sum at the index L and R, okay, R plus 1 to be precise, and after we are using prefix sum to build the whole array. So these are somewhat like a partial value that you have kept at those indexes and later on you are going to use that. So that's why this idea is called partial sums, okay? And so that's all for this idea. You can use this idea in things which support prefix sum. So any operator that you could support using prefix sums, you can even use partial sums to do their range contribution or range update kind of things. So these queries are range update, right? You update a range, so you can support range updates. The only thing that you need to be careful about is that in this problem you needed the final array only, right? You needed the final array. If you had to ask the value at a particular index in between the queries, you would not have been able to support that, because or else you had to build this prefix sum. So that is not supported using this. But if you had to build the final array after all the queries, this is the technique that you can go to. So that's all for this partial sum technique. Thank you and see you in the next video.